Hello students, in this video we'll discuss basic properties of the diffusion equation and use it to generate a family of self-similar solutions. So let's consider the 1D wave equation, or the 1D heat equation. Which is just ut is equal to k u x x, right? And let's assume this is defined just for x between negative infinity and infinity on the real line and t greater than or equal to 0. Okay, so there's the whole real line for the diffusion equation. So what are the basic properties of this? The first property, property 1, is that if u of xt is a solution, then tau y of u of xt, which is u of x minus y t, is still a solution. So I can translate solutions and get a solution. That's a very, very useful fact. So if I translate the spatial variable, I still get a solution, okay? What's the next property? Property 2. Okay. Property 2 is that if u of x of t is a solution, then I can do any number of derivatives, m plus n, partial x to the power m, partial t to the power n, any number of partial derivatives of a solution, if assuming that, of course, I give you a smooth solution, right? You will also solve the equation, is also for n and m and n. So for any number of derivatives, any derivative of a solution is still going to be a solution. That's just clear because I can just differentiate that equation at will, right? Good, that's property 2. What's property 3? Property 3 is trivial also. The 1D heat is a linear constant coefficient equation. Okay, if k was not constant, right, so here we're using the fact that k is constant. In our problem, we're always going to assume that k is constant. When k is not constant, we get really interesting mathematics that happens. In fact, it's really interesting when k is a jump, right? If k is a jump, then it's really, really interesting because you get sort of very different behaviors, right? But of course, that is going to allow me to use Fourier analysis too. So we already done our course in Fourier analysis. We can sort of circle back to our Fourier analysis results, and now we can make sense of this. Okay, that's property 3. Is that it's a linear equation. I can shift solutions, and then what's the next thing to do? The next thing is I can use convolutions, right? So property 4 is that if S of x and t is a solution, then if I integrate over R, S of x minus y comma t, with any sort of reasonable function over here, with any sort of smooth function g, is also a solution. And we're going to use this one a lot. In other words, if I give you a solution, I could do a convolution of a solution with a reasonable function. I'm not specifying what regularity I need in g just yet, because it's a little bit technical, right? I can get into distribution theory like this very quickly. Let's leave it like this for just smooth functions, okay? So in other words, I can do convolutions, right? Excellent. And then what's the last one? The last one is the most important. It's the scaling, right? Property 5. You might say, well, why did you do scaling last? Because property 5 is going to get us something interesting, right? So in other words, if u of x of t is a solution, then so is what? Then so is u of lambda x and then lambda squared t, right? That's the scaling of the equation, okay? And what this allows me to do is this allows me to choose a particular value lambda. If we choose lambda to be 1 over the square root of the 4 is just an annoyance for kt, then what we can do is I can define variables. I can look for a function. I can define a variable xc to be x over the square root of 4 for kt. That's my new variable xc, okay? And let's consider phi of xc, right? So phi of xc, and I would like to figure out when phi of xc solves the heat equation, right? When does this, because this is a function of xi, but that depends on x and t, right? So when does psi when this phi rather, 1d heat. Okay. Well, of course, we can just simply check the t derivative of this thing. So if I call this expression over here u of x of t is just this, then what would ut be? Then ut over here is going to be what? It's just going to be, I'm just going to have a negative 1/2, 1 over 2t, and then x over the square root of 4kt times phi prime, right? What would uxx be? Uxx would just be what? Well, I would have a 1 over 4t, 1 over 4kt, phi prime prime of xc. Okay? And so therefore, what do we have, of course? Therefore, that's, of course, just an xc, right? And so we have the differential equation over here, then this would imply that it would be a solution. So what we're going to have over here, so we're going to have, let's see, so ut minus kuxx is just going to be a negative what? Let's see, so I'm going to have a 1 over t, a negative 1/2 xc, phi prime of xc, and then minus 1/4 phi double prime of xc. I need to set that to be equal to 0. And now we're in a good shape because that's just a second order differential equation. There's going to be a constant solution, right? And then if I integrate the constant out, then I'm going to have to figure out what the solution of this is over here. So, right, so if I do one integral of this thing, I'm going to get that's the key feature of this over here, is that we can get a factor of, we can solve this differential equation explicitly. The solution to this, by solving the differential equation, is going to be what? My phi of xc is just going to be what? It's just going to be a constant c1 plus the integral from a constant c2 up to xc of e to the negative x squared, or I should put x squared, I should put a different dummy variable over here. Let's put a different dummy variable. Dummy variable is going to be e to the what? E to the negative, let's say eta squared d eta, okay? So in other words, functions of this form are going to be the self-similar solution. So these are self-similar coordinates. And all I've done here is I've just solved the second order differential equation. Clearly a constant's going to solve this. I have a second derivative and first derivative, so integrate a constant. Then I have a differential equation that looks like phi prime plus xc phi. Well, of course, that's just as the logarithmic derivative of phi prime is equal to xi, right? And of course, if I integrate that, I'm going to get xi squared, right? When I integrate xi squared, therefore I'm going to get a what? Then I'm going to get an antiderivative of something that looks like e to the negative xi squared. Okay, excellent. So these are self-similar coordinates. And we're going to see in further videos of these self-similar coordinates by finding these constants c1 and c2 for a particular sort of test function that we're going to use to recover this convolution identity. We're going to see that that's going to help us to find the fundamental solution to the heat equation, and that will give us the general solution for sort of a wide class of G, which we'll see in further videos. Thank you very much.